Good afternoon. I hope everyone's doing great. Do you have any questions I'm going to ask you at the outset? Because otherwise I'm going to plow ahead. I'm going to complete this question that's being displayed right now. Then I'm going to answer question 2 in this practice assignment. And then my plan is to talk about Bayes' rule. Tomorrow you will have a quiz and I will introduce the assignment problem. So we'll meet at 5 for me to do some lesson. Then the quiz will be at 6 online. And also online you'll find the assignment problem. Hello. Okay, so no questions. I haven't gotten any emails from anyone about questions. Maybe you're really fine with this, or you haven't had a chance to review it, or you're busy with other classes. I hope it's straightforward. I've given you lots of problems with solutions or answers, so you have a lot of material to review. And this assignment is very good as well. The 2 topics that remain, the Bayes' rule and the topic on the means and variances of random variables, sums and differences, that I'll talk about tomorrow, I guess, and Friday if I need it. All right, so if you don't have a chance to watch those videos, you can pick them up later, but the quiz tomorrow will include everything up to Bayes' rule. Question 9 from homework. Let's see. Question 9 from the homework. I got a question. If you've tried the quizzes online, there's a lot of Bayes' rule problems in there. The homework. All right, so what you have to do there, the trick for number 9 is, I'll cut and paste it. Oh, it won't let me paste it for some reason. Oh, it's too big. Okay, many random number generators allow users to specify the range of the random numbers to be produced. Suppose that you specify that the range is to be all numbers between 0 and 2. And that's because call the random number generator y. The density curve of the random variable y has constant height between 0 and 2. So this is a continuous variable, right? From 0 to 2, you have all those possibilities. It could be 0.0001, it will be there. Now this is referring you to the uniform distribution. Basically, this is a uniform distribution problem. You got to make the rectangle, in other words. Okay, so you got to make, for this problem, you got to create a rectangle like this between 0 and 2, and it's uniform. I know it's uniform. It doesn't say uniform, but what it does say is that the density curve of the random variable y has constant height between 0 and 2. So that's why it's like that. It's just a rectangle. Okay, so then you use that to find the probability between 0.6 and 1.7. Okay, so that's it's illustrating. Well, it's illustrating in words, or it's describing in words without an illustration. So maybe you're confused. So try that. Okay. Any other question? You can ask me again if you still don't get it after that try. Okay, so I'm going to pick up where I left off. That was in part D. Find, we already did this. And we found out that A and B were independent. Okay, you can look at that video from yesterday. The next thing is to look at events A and C and check, are they disjoint, are they independent, or neither? Okay, remember the 4 possibilities, they can either be complements, disjoint, overlapping, or independent. Those are the possibilities. And the other one, actually there was a 5th way that 2 events could interrelate, and that was where that was in the exercise that I provide a video for, where, well, actually I won't say it here, but there's just 5 ways that they can relate. So make sure you watch the videos in the Moodle page. Okay, so let's look at A and C. So here I've presented the 3 different events, A, B, and C, and B and C is what I'm interested in now, right? That's the question, or A and C? It's A and C. Okay, so I'm interested in A, which is red, and C, which is the black. Now, do the red outcomes and this single outcome ever overlap? No, they don't. In fact, these events in red and this event in black are mutually exclusive or disjoint. So you can just see that from the drawing. That's all you have to say. Right? So you would just say A and C are disjoint. You're going to write it nicer than I will. Just say these are disjoint. Okay, because they have no overlapping outcomes. Let's see B and C. B and C. Well, A and B were independent. A and C were disjoint. So what about B and C? B and C. So B is the blue. So B is the blue. And C is the black. Do they overlap? Yes. They're not mutually exclusive. They're not disjoint. They overlap. So that's the next question is, since they're overlapping, got to check, are they independent? What does independent mean again? It means if you know that an outcome is in the blue, does it change the chance that you're in the black? Okay, that's what independence means. In this case, what you see is you're going to basically check. So I'm going to do this a shorter way. I'm going to say probability C. Let's check. If these are the same, then they're independent. Okay, so this is saying if it doesn't matter that I'm already in another event, or I'm looking at another event having occurred, if these 2 outcomes are the same, then they're independent. Well, let's see. So C is 1 over 20. We know that. We computed that. It's just 9 or whatever. We just knew that. So That's this, right? And B given C means what's the chance if you're in the blue outcomes, the blue set of outcomes representing B, which was an odd sum. If you're in the blue, what's the chance that you're in C? Well, out of the blue, so now we're going to use the subgroup. Out of the blue, only one is in C. So how many outcomes was this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this means that this is the subset. There are 10 outcomes, and only one of them is C. All right? So basically, when you put a given statement here, you're looking at the subset. So I'm just looking at the blue outcomes. There's only 10, and only one of those are also C. So in fact, when you go to the smaller set B, the possibility of seeing C is affected. It goes from 1/20th to 1/10th. So in this case, C and B then are not independent. They are just overlapping. Okay? So you can say, what were the options again? The options are disjoint. They're not, because they overlap. They're not independent, so they are neither. You can say not disjoint, not independent. Okay, they're just two overlapping events. I hope you got that. Let me know if that makes sense. I could have done this the other way that I did it last time, where I checked. So that's one method, to do it. I could have also said, let's check if probability of B and C is equal to the probability of B times the probability of C. And you would have shown yourself you would see, and I'll leave this for you, verify this for yourself, that B and C is not going to be equal to the probability of B times the probability of C. Okay? B and C is just that overlapping piece, the 1/20. It's just this one. So overall, right? Because I didn't do any. Right now, I'm not making any statements about given a certain subset. I'm just saying overall, what's the chance of B and C happening at the same time, where the blue and the black overlap right here, and that's 1/20 total. But that's not going to be equal to B times C. Okay, because B is already, B was 10/20s. If you multiply by 1/20, this is 1/400, or it's 1/, sorry, because that's a half, that's 1/40, so they're not going to be equal. all I'm doing there is multiplying. Okay, those are two different ways you could say. There's two different ways you can prove that. You can just work with the statement here and show if they're independent, these should be the same. Since they're not independent, they're not the same, sorry, they're not independent. All right. That proves that. They're supposed to be the same. Okay, so these are not equal to each other. They need to be the same. Therefore, they're not independent. And then these also need to be the same because this result comes from this result. And they're not because, anyway, how much more can I do this? There's just two different ways of showing the same thing. Do I have to explain this again? Okay, so the point is, again, what is independence? It means it doesn't matter if I'm in the subset of B. It doesn't matter if B already happened. The chance that C happening stays the same. But here, in fact, this is the probability of C, and this is the probability of C once you've seen B happen. And they're different. So it does matter. It does change things. So that's why they're not independent events. Okay, I'm going to save this. You guys can work with that. Now, independence, again, is a very specific thing. It's not common for events to be independent. I explained for the salon case, there's no reason why the chance that I get my hair colored if I've already gotten a manicure would be the same. The chances that I'm going to do two services after I've done one, the chance of the second one goes down overall because I already spent money. That's one argument, one consideration. So, all right. So let's see. We've done the rest of that. And now I want to look at this problem, number 2. So if you draw one M&M candy at random from a bag of candies, the candy you draw will have one of 7 colors. The probability of having each color depends on the proportion of each color among all candies made. Here is a distribution for milk chocolate M&Ms. Okay, so what must be the probability of drawing a blue candy? How do you figure that out? Well, these should all sum to a total of 1. So all that's missing, this is 2, 4, 6, 8, 9. So this has to be 1, right? Because 0.1, because that's all that's missing to make 1 total. 2, 4, 8, 10. Okay. Part B. What is the probability that you do not draw a brown candy? Well, I could write this really fancy. Let's see if I write this up fancy. Probability of not brown, so I'll use the bar, is equal to 1 minus the probability of a brown candy. So then that's 1 minus probability of 0.1, which is 0.9. That's it, 90%. Now you don't have to write all that, but it's nice to show me your effort for part marks. What is the probability that the candy that you draw is either yellow or orange or red? So probability of yellow or orange or red. Since it can only be one of these, we're going to apply rule number, I guess that's rule number 4. Addition for disjoint events. They don't overlap. It's just one or the other, or means add if they're disjoint. So I'm just going to add the probability of each. So that's 0.2 or 0.1 or 0.2. So just sum them. That's 0.5. So it's a 50% chance that it's one of those. It's easy, right? That wasn't hard. I thought it was more challenging. Okay, so those are the probability rules. We've applied them. Okay, so all I want to do now, what I want to do now, if you don't have any questions, is go to Bayes. Okay, conditional probabilities and Bayes' rule. Let A and B be two events with probability A and probability B. In general terms, if A and B are not independent, okay, because that's the general case, nothing special between them, just overlapping events, then I can find the probability of A and B, provided they overlap. Right? If they didn't overlap, this would just be 0. If they were disjoint, in other words, this would just be 0. So if they're not independent and they're not disjoint, this is how you calculate the probability. The probability times A, the probability of A. So A happens, of the chances of this happening. So you can multiply that by the probability of B given A. All right? So that's how you calculate it in general. You could also compute it with sorry. Oh, no. Anyway, let's see. This, I could also compute it. I would get the same answer if I did look at B happening first. And I multiplied the probability of A given B times the probability of B. Those should all be the same thing. You can go back and think about my example with women in a salon. And there's other examples. So we interpret that as event. So if I gave you numbers, right? So let's say event A has, like we looked at before, event A has a 30% chance of occurring. 30% chance of occurring. And of those times, event B will occur, B given A% of the time. So that's why this of implies I need to multiply. That's why I multiply. Oh, sorry, here. I'm using that form. Okay. Also, we can algebraically, if you just look at these terms here, it's possible that I don't have that information. It's possible that I don't have the information on the event B given A. So I don't know about the situation in the salon where women will have gone in for a manicure, and I want to know what's the chance that they also go in for, they also have a hair color. So looking at A and B is just them happening coincidentally. But could I solve for what I just stated? Them having a manicure already, what's the chance they actually get a hair color? That's a different number than this. All right, and actually this makes a lot of sense. This is exactly like the calculation I showed you before. I'm going to use this subset. This is my denominator, you know, the outcome, the possibility of A happening. And out of that, the chance of seeing A and B. Okay, so this number and this number are different numbers, but they're related. So you need to get that in your head. So this is going to be the challenge in solving these problems. Like I mentioned, there's quite a few quizzes that test you on this online. So this is very practical, given what we're going through right now with the the COVID, I'm going to call it the SARS-CoV-2 virus, to be technical about it, that relates or is possibly going to lead to COVID-19, the condition. You could ask the question, what's the chance that people had a false positive test? So they tested positive, but they're not really positive. So that's called a false positive. Now this is the vocabulary that Bayes uses, right? This is, so let's look at this. So this is very practical given what we're experiencing right now. Let's see, I'm just going to be more general about this. So example, 2% of the population has a particular disease. Okay, so let's say at any point in time, the prevalence is 2% of a disease. You can think of the COVID-19 as a disease. However, 3.2% of the population tests positive. So there's a mistake, right? There's some error there. 2% have the disease, but 3.2% tested positive. Assuming we tested everybody, I guess. In other words, a test for the disease is not perfectly accurate, and that's always the case. From a population-based study on people with the disease, it was found, so this is a group of people who have the disease, so that's why this given is here. The disease test, the positive doesn't mean test positive, so maybe that's not the greatest notation, but it means that they do have the disease. A minus means they don't have the disease, okay? So it's found that 75% of them tested positive, okay? So that's the lingo. Given that I'm looking at a group, a subgroup that has a disease, the chance of having a positive test turns out to be 75%. What we really want to know from that, all that information I've given you, all those percentages, what we really want to know is if someone got a positive test, what's the chance they really have the disease? Like I said, it's all very relevant. So that's what we want to solve. To solve that, I made a table. The table actually, maybe it's too much information. We can just do this simply here on the side. I can write this. I'm going to make this bigger. So I could find this according to what was discussed up here. I could find this using this expression. Okay, so this is a new formula in the sense, I mean, you haven't seen it like this before, but it draws from the definition or the relationship between, it draws from this. Okay, so this is the relationship between conditional probability and intersecting overlapping events. So let's see, let's translate from here. I want to exploit this expression to find this. So how do I find this? This is going to be the probability of a positive test and the disease divided by the probability of having a positive test. Okay, so I'm going to look at the subset of people with a positive test, and out of them, using that as a denominator, what proportion actually have both the disease and the positive test? Do I have this information? Do I have the information on the probability of a positive test? Do I have the information on the probability of disease and a positive test? Let's see, what do I have up here? So there's a lot of percentages floating around. What is this one? So that one's just the probability of a disease, of having a disease. So this is B of disease, is this one. What about this one? 3.2% of the population test positive. Aha, so that is the probability of a positive test. So I have those two. And here I have 75% of them, of the people with the disease, so given they have the disease, they test positive, and that's that one. So I don't have this, do I? I have this, but I don't have this. Now, how am I going to find that? Creating this table can help you find it. Okay, this is the table. This is a joint probability distribution. We've seen this before. I just have 2 and 2 though. Before I had gender along here and then occupation here, but it's just 2 by 2. And can we fill it in? So this is all that we know so far. We have all this information that I explained above. These represent all your possible outcomes. So what I need is both the disease and that they have the disease. Sorry, the disease and that they had a positive test. This one. So we can go through the trouble of computing all the entries, but I really just want to focus on this one. How am I going to get that one for my formula? Well, we're going to go back above because their formula, the other formula, was right there. So this is like this is all you need. You just need this expression that extends into this version here, and this variation of the formula. Okay, that's all you need to do this. If I want to find D here, I want to find the probability of the disease and the positive test. I should expand it into this version, and I have the numbers for that. I have all the data. So you see all this stuff that you need to be able to know the meaningfulness of a test. So if I expand this in a way, for the values that I have, I know that this is the probability of positive test given they have the disease, because I have that number, times the probability of the disease. I have all that, you see? And I'm going to divide it by the probability a person tests positive. So if you feel like you're in the twilight zone, or I somehow pulled a trick on you, it does feel like that. But if you appreciate this, you see the power of conditional probabilities. So all you needed to know to find out the chance, what it means when a doctor says you tested positive, what is your chance of actually having the disease? It's not 100%, all right, because the test is not perfect. So we need to compute from here, using all this data that we have. I have this, I have this, and I have this. Look at that. So what do we compute? It's going to be the conditional 0.75. That's the group of people who have the disease, their chance of getting a positive test. And then actually having the disease is 2%. And then the chance of a positive test, which was 0.032. And that will give you your answer. It's a very low number, isn't it? So in this scenario, what do you get? I'll give you a minute. So we need all this data. It's data that we don't have. I've been pressing whenever I have a conversation with friends who are statisticians, epidemiologists, economists even, that we don't have these numbers for the COVID-19 case. We don't have these population data, and we really, really need them. So if it's possible to get some funding for Puerto Rico to do a study, it should be to take a population, see how many have the disease, see how many actually tested positive for the disease, having the disease, to see the accuracy of this test. So we can tell people, you tested positive, so you must have the disease. It's not 100%. Did you compute? I'm waiting for you guys. So I get 0.48675. 40, so it's like 50%. So you get a positive test with this data about the accuracy of the test. You get a positive test, you have 50% chance of actually having the disease. Very important information. That's what really bothered me when I heard about Angelina Jolie having these genetic tests done. You know, the actress, she had these genetic tests done. I didn't know the accuracy of those tests, but they're not perfect for sure. And with the results of those tests, she believed she had to take preventive action against cancer, and had a number of surgeries to remove organs in her body. And I just felt like, you know, knowing statistics, did someone explain this to her? It might not be the case. She actually has the disease. So that's information for you, I imagine. And this is the power of statistics. It's aggravating too, because most people don't know this. And it's really important, whatever test it is, ask your doctor to tell you. And even if he's not a statistician, he should know what the meaningfulness of a test is. Okay. In the case of COVID-19, we just don't have this data to make these kinds of statements. But we're assuming everyone has a disease. Oops. All right, let's see. So I asked to make the table. You can work with completing that table just for practice, but I got my answer already. My answer to the question. So that's how Bayes' rule works. You just have to expand. In this case, all I expanded was the numerator. So using conditional probabilities, I can solve for other conditional probabilities. This is a lot longer. So the top is what I did. I flipped the conditional probability on the top, but I didn't do the bottom. But you see, what is the bottom? What was it over here? Let me put this up. the bottom was just the probability. So on the other page, I just had the probability that a person had a positive test, the subset, right? So this should always be the same. This here, this given or conditional is always the same as the denominator because I'm looking at the subset of people. So that's going to become the denominator. Now this is equal to all of this. Why? Why is this equal to all of this? Think about it. What does this mean? What does this mean? This means the probability of a positive test and, the probability of having the disease and a positive test. That's what that means, right? If you look back at the formula, this can be written this way, right? This is what and means. It means I take the probability of one event happening, and then given it happens, what's the probability of the other? That's multiple is this. I could also have written it as conditioned on the test result, but I didn't want to here, because what I want to do is do the same thing for this one. What's this? This is probability of having a negative test and, not having the disease and a positive test. Together, either this happening or this happening, the probability of this happening, the disease and a positive test, or this happening, or with a plus, no disease and a positive test, is the same as saying positive test. So those are the possible outcomes for a positive test. Okay, so if you follow me, this and this together make this. I can expand those further if I need to. I didn't need to in this case because I actually had this number. We had this number, so I didn't have to expand. All right, but Bayes was the statistician that pointed out, wow, look at how we can use conditional probabilities and their reverse, events to calculate estimates. Okay, so this is fascinating. It looks a little bit messy. It's better for you to try and understand it than for you to memorize it. The only thing you should memorize is that this point here at the very beginning, that I said since we started this unit, this is what you need to know. You need to know that in general, the probability of A and B is equal to the probability of A, and of those times, given A happens, the probability of B. We multiply those together, or we can do it this way. You'll get the hang of it if you do exercises, if you've ever done anything like this before. It's very practical that you be able to do this. I'm going to leave it there with the Bayes rule, but there's much more we could do with Bayes, and if you go on in statistics, you're going to learn about what's referred to as updating, like information. So once you know something happened, you can upgrade your probability and your estimates. Anyway, we're not going to work with that here because this is just an intro course, but it's the recent developments using Bayes. All right, so you can read through that, you can try the exercises, and that brings us here. So I made videos on this topic already, but I don't think the students found it very useful because I think I just read through the notes. it's much more useful for me to illustrate this, because you can read through this and accept it, memorize it, but I don't know that you really have a very good sense of what's going on. Let's start. Okay, let's just start here. So what we're going to do here, I'm going to introduce you to the rules for means and variances. What am I talking about? Well, since the beginning of this course, we have focused, well, initially in the first unit, we talked about skewed distributions, right? And we talked about symmetric distributions. Then, ever since the first unit, the second unit, GDS, I turned and I said, well, when we started in the normal distribution, I said we're going to focus on symmetric distributions and particular normal distributions. So we did that for a while. Then in this unit, I introduce you to the idea of what was I going to say? Oh, yes. So I went through and discussed the different kinds of variables. So discrete distributions, discrete variables, and then continuous variables. And I gave you examples of the ones we're going to discuss in this course. So let's say you have information on a variable. In particular, you know its mean and standard deviation. Since you know its standard deviation, you also know its variance. But imagine that there's something, so I present these different scenarios, and so this is a scenario. I'll start with the example. These are the outcomes, and these are their probabilities. Now, this is a discrete distribution in that I can actually list. When I can list out the possible outcomes and their probabilities, this is discrete, right? This is a discrete distribution. I'm not going to get into continuous distributions because what that involves is that you are able to do calculus, which is not assumed for this course. So it doesn't matter because the rules that I'm going to show you for what we want to do are going to carry to continuous distributions as well. But to illustrate what this is about, this example is given to you discretely. So these are the possible outcomes for this setting. Suppose an individual plays a gambling game where it's possible to lose $1, break even, win $3, or win $5. The probability of each outcome is listed here. You can actually calculate the mean. Remember, if you have data like this, you could calculate the mean as the weighted mean, right? Different outcomes with different possibilities, then I have to calculate a weighted mean. And that's what's being done here in this calculation. So the weighted mean is 80 cents. Right, so you multiply this times this, plus this times this, plus this times this, plus this times this, and you get 80 cents. In the long run, then, the player can expect to win about 80 cents playing this game since the odds are in her favor. We refer to the law of large numbers. Remember, we discussed the long run. The long run relative frequency is what probability is. If we try enough times, we're actually going to see this happen. We're actually going to see that 80 cents is going to be the average on any game that she plays. Maybe sometime she's going to make a lot more, maybe sometimes she's going to make a lot less, but on average, over enough games, she will have made 80 cents a game. Okay? That's referred to as the law of averages. Okay, so this is just a way, so we're going to begin with this example. And now I'm going to vary this, I'm going to change the setting. I'm going to make an adjustment to this distribution, and I'm going to do it in a systematic way. Next page. Here it is. What we're going to do to adjust this game, since this person is winning on average, right? Like the person's winning 80 cents on average after many games. That's not good for a casino. So the casino needs to make an adjustment. So the adjustment is going to be they're going to subtract all the payouts by $1 for each prize. All right? That makes so if it's $1 for each prize less the 80 cents, it's going to bring down the average of the person playing in the long run to losing at every game. So what's done here, the adjustment was just subtract every possible outcome by $1, leave the probabilities in place. This is my new distribution. And this is my new mean. Okay, so this is the thing. You could do this. You could sit, you can calculate all the possible outcomes, recompute the mean, but shouldn't there be a relationship between this mean and the other mean of the original distribution? Well, in fact, there is. All right, so if, let's say, let me do this, even though the example is discrete, I'm gonna look at, let's say we're going to talk about a curve distribution. It doesn't have to be exactly normal, but okay, so there's my distribution, and here's my number line here. This is my number line. Or actually, you know what I should do? I should actually put it over here. There's my distribution. Oh, it's not perfectly normal, but it's, you know, bell-shaped, symmetric looking. And all the possible outcomes here are listed. These ones are more likely, the ones in the middle, a few out here, just as many few out here. If I take every possible outcome, like I did here, and subtract one, in this case, let's say subtract a constant amount, that will shift the distribution over by 1. So let's say I call this x. So we did something like this, right? When I worked with the normal distribution transformation to the standard normal. So let's say I take x, the distribution, and I subtract, subtract something from it. Let's say 1 or 10. It just shifts it over, right? It shifts it over. So what happens to the mean? That's the question. The mean was here. This is the new mean here. My question is, what is the relationship between this mean and this mean? Should there be a relationship? Well, every value was subtracted by 10 to move this over here. So I moved every single value over 10. Same shape. This should be the same shape. I didn't change the shape. Well, if I do that to every single value, then I also do it to the mean. Okay? So a transformation that subtracts or shifts a distribution over also shifts the mean over. And this is true, right? The the 80 cents minus 1 is negative 20 cents, or a loss of 20 cents. So that's what happened. So the mean was originally 80 cents. You have to subtract it by $1. To get the 20 cents. Okay, so why do we care about this? Because I went through a lot of trouble to derive this distribution. Likewise, someone went through a lot of trouble to derive this distribution. So it's a matter of observing many times, collecting data, grouping the data, recomputing or redrawing the distribution every time, collecting that information, waiting, all those delays. Why should I do that? Again, well, I know there's a pattern. Whatever I do to each value of the distribution, I also do to its mean. So I don't have to do that. I don't have to wait for data to see this pattern. I know what's going to happen. Okay, so this is the rule for means. And there's a little bit more, it's a little busy here what this is saying. This is just saying, this is, don't get intimidated by the notation. The notation's meant to help you. So if it intimidates you or confuses you, just ask me what's going on. So throughout this exercise or discussion, I use these symbols that remind you of population, right? This is the population mean. Why am I using these symbols? Population mean. I'm using the symbol for the population mean because, in fact, I've given you information on the population. This is the distribution for the population. These are all the possible outcomes. This is not just a sample. This is information about the entire, all the possible outcomes. There's only 4 possible, and this is their probability. So this is the population. So that's why I'm using those symbols. So what this is saying here is that so the symbol here, E is like the expectation operator, called like an operator. When I take the E of a linear transformation, see, this is a line, this is A plus BX, which you should be familiar with, but in this context, I'm shifting by adding, well, we subtracted 10, or we subtracted 1 in the examples below. But I'm going to shift, however, A can be a negative. X, now this is this B here. What is happening here? Well, this is multiplying the variable, every value of the variable, and then this is adding. So we just looked at the adding part. What would multiplying the variable do to the mean? Let's go back down and look. It's more straightforward in the continuous case, I think. So let's see. So this was the case of this is like a subtraction, okay? So this is looking at the shifting. This is the A part. And then there's the scalar. the multiple. Okay, the multiple is the B part. Again, let's say I start with that distribution. And let's say I multiply every single value by a number. Up here, A was, the shift was -10 in my example. Let's use a multiple of B let's just use 2. Oops, where did everything go? Okay. Let's use a B of 2. So we're going to multiply every single value by 2. What happens? If I multiply every single outcome by 2, what does it do to this distribution? Well, let's just start in the middle. Always start in the mean. What happens to the mean? Well, if I multiply the mean by 2, the mean becomes two times 0.8, right? So I'm going to draw that over here. So let's say I had this 0.8, and then I multiply that by 2. So that's going to move me along here, the number line, if we're going to use the number line. Well, actually, that's not the drawing. I'm just moving one at a time. So this will be at 1.6 now with that height, right? And what about all the other values? What's going to happen to something like this one over here? Well, that's going to be doubled as well. So it's going to be further out. So let's say this one was, so imagine this is like just a distribution. I'm not relating it back exactly to what we just saw as discrete. This is a continuous case. Let's say this was 1. So what would it become? Well, it would become 2. So this gets, what's happening is this is going to spread out more. All right, so when you multiply each value of possible outcomes, sorry, this is too low. Well, it should flatten as well. I need to bring that down. It's going to do this. So every value will be here. I still have to have the same 100%, right? So it has to flatten the curve to accomplish this. So this is going to be 1, this is going to be 2. If this one was 0.6, this one would be 0.6 times 2 is 0.36, right? No, 1.2, sorry. It will be 1.2. So I'm convincing you, I hope. So this is going to spread this out, flatten it. That's the result of multiplying. Okay? I can also multiply by a fraction. In other words, I'm dividing by a number. By dividing by a number, you're going to shrink it. If b is equal to if b is equal to 1/2, 0.8 becomes half of that. It's going to so it's going to shift, but in the opposite direction, okay? And every number will be smaller. So it's going to shift and it's going to shrink. So the effect of the multiple is it's going to shift and it's going to flatten if it's greater than 1. If it is less than 1, or in other words, we're dividing, it's going to be, the 0.8 would be 0.4, it's going to shift left, and then each of the numbers, like 1/2 would become, this 1 over here would be 1/2. So these are going to end up being closer together. Do that again. So it's going to end up being like more like this. Well, much more smooth, but much more peaked. That's not a very good drawing because I need to make it peaked. It's going to be more squished together, much narrower, with 0.4. And then 0.5, it's very tight. It's going to be tight like this. Okay? So my point of showing you this is so you can think, even though the exercises in the notes are all these numerical discrete distributions, a shift is caused by adding or subtracting the variable of the distribution, or the variable, and you spread it out when you multiply by a number greater than 1, and you flatten it when you multiply by a number greater than 1 and less than 1, or anyway a fraction, let's say it like that, less between negative 1 and 1, that would just narrow it as this has. Okay? Okay, so this is what this is talking about here. So what you got to remember is, this is all you have to remember. You never have to write this formula out or anything like that. You just have to remember when we know about a variable from another variable, and the relationship is a linear, we call it a linear transformation. So something's been multiplied to the original variable. Sorry, here I'll show you. Or something's been added, a value's been added to the original variable. The mean will be affected in the same way that each value of the variable was affected. That's all this is saying. Okay? So the mean of a linear transformation is the linear transformation of the mean. Whatever you do to each value, you do to the mean. Okay, so I'll stop there, and I'll pick up here tomorrow But on the quiz, you can do everything up to and including Bayes for the quiz tomorrow. So work on that. There's exercises for Bayes in the online quizzes. You can practice those. Okay, let me know if you have any questions. Have a good night.